points than other organic compounds of comparable molecular weight.
The boiling point of straight-chain alkanes increase in a smooth progression as the length of the carbon chain increases. See the graph on the screen. At standard temperatures and pressures, straight-chain alkanes with 1 to 4 carbon atoms are gases. Those with from 5 to 20 carbon atoms are liquids. And those with more than 20 carbon atoms are waxy solids. Cycloalkanes show the same steady gradation of boiling points as straight-chain alkanes. If we plot the boiling point curve for cycloalkanes, we will see that their boiling points are slightly higher than those of their normal counterparts. This is due to the stronger attractions between molecules. Since the electronegativities of carbon and hydrogen are similar, at 2.5 and 2.1 respectively, alkanes are non-polar substances. Their molecules are attracted to each other only by weak London dispersion forces. The forces between molecules of the low molecular weight alkanes are very weak. Larger alkane molecules give rise to stronger London forces. As the alkane becomes larger, more energy is needed to separate neighboring molecules, and so the boiling points show a steady increase with molecular size.
Branched-chain alkanes do not show the same steady gradation of boiling points as straight-chain alkanes. The variation in molecular structure of branched-chain alkanes is too great for trends to be clear. The effect of branching is to increase volatility. Thus, the boiling point of hexane is 69 degrees Celsius, while that of its highly branched isomer, 2,2-dimethylbutane, is 50 degrees Celsius. Chain branching makes a molecule more compact, decreasing its surface area, so decreasing the van der Waals forces. The more volatile the substance, the lower its boiling point. Alkanes and cycloalkanes are only slightly soluble in water. Water molecules interact with one another because of the strong hydrogen bonds between them.
The hydrogen bonds formed between water molecules are stronger than any interaction which can occur between water molecules and the non-polar alkane or cycloalkane molecules. Dissolving is therefore not energetically favorable. All alkanes and cycloalkanes have densities lower than water. That is why liquid alkanes float on the water surface. These two properties, insolubility in water and lower density, are responsible for the well-known and serious effects of oil spills from ships.
Liquid alkanes and cycloalkanes are soluble in one another. Also gaseous and solid alkanes can be dissolved in liquid ones. A good example is petroleum. Good solvents for alkanes and cycloalkanes are those with low polarity, like benzene or carbon tetrachloride. There are only a few types of reaction known for saturated hydrocarbons. One of them is radical substitution by a halogen. Another one, which is indeed quite violent, is the combustion of alkanes. The general name for the reaction of alkanes with halogens is halogenation. It can be exemplified by the reaction between methane and chlorine. The reaction consists of several steps.
The first step is the homolytic fission of the chlorine-chlorine bond to produce chlorine atoms. The energy necessary to break the bond comes from light. This step is called the chain initiation step.
Chlorine atoms are very reactive. Since they're surrounded by methane molecules, there are two possible reactions. Either chlorine bonds to a carbon atom to form chloromethane and a hydrogen atom, or it binds to a hydrogen atom to form hydrogen chloride and a methyl radical.
The methyl radicals formed collide with chlorine molecules to form methyl chloride molecules and chlorine atoms. In steps 2A, B and C, further radicals are being formed. These steps are called the chain propagation steps. Thousands of methyl chloride molecules are formed for every photon of light absorbed. Radicals can also combine with each other to bring the chain to an end. There are three possibilities for ending the chain reaction. 2 chlorine atoms combine, 2 methyl radicals combine, or a chlorine atom combines with a methyl radical to form methyl chloride. This step in the reaction mechanism is called the chain termination step, and the overall mechanism is known as free radical substitution.